Hi, let's continue with the lecture on the topic of kinetic. Last week we have seen some of the topic related to the rate of reactions, and today we are going to look into these instantaneous rates. So instantaneous rate taken near the beginning of the reaction at time t equals to 0, and it is known as the initial rate, as labeled here as 1. So as we shall see soon here, the initial rate plays an important role in the study of reaction kinetics. If you have studied differential calculus, you will know that these tangent slope are the derivatives whose value can be varied at different time points on this curve. So these instantaneous rates are rely on the limiting rate defined as the equations given here, where the rate is equals to the limiting when delta t is approaching 0, meaning that if the changes of the time is very small. So it is equals to the change of the concentrations to the change of the time. The negative shows that the decreasing of the amount for the reactant. So this tells the rate of reaction depends on the concentrations of the reactant. Therefore, the reaction rates can be determined over a particular time intervals or at a given point in time. A rate law describes the relationship between the reactant rates and the reactant concentrations. Reaction rates are usually expressed as the concentrations of the reactant consumed or the concentrations of the product formed per unit time. For a general rate law, as you can see from these expressions, the rate equals to the differentiations of the product at different time equals to K multiply concentrations of A to the power of X multiply concentrations of the reactant B to the power of Y. X and Y are the order of the reactions. The overall order of the reactions is equals to X plus Y, whereby K is a rate constant, and rate constant is with the unit with the value of positive, and the unit will be depends on the overall order of the reactions. The unit for the rates are therefore can be written as mole per liter per unit time. It also can be translated as a molar per second, molar per minute, or molar per hour. So usually to measure the reaction rates, chemists will initiate the reaction, and then we will measure the concentrations of the reactant or the product at different time. As the reaction progresses, then plot the concentration as a function of time on a graph. After that, calculate the change in the concentrations per unit time. So the reaction, it has a different order. A reaction is first order if the rate is proportional to the first power of a single reactant. So in this case here, if x equals to 0, then y will be equals to 1. Or if x equals to 1, then y has to be equals to 0. So the rate will only depends on one of the reactant, and it is known as the first order reactions. Whereby for the second order reactions, we have the x equals to 1 for the reactant A, and the order for reactant B, y will also be equals to 1. So the total rate or the order of these reactions will be second order. We can integrate the rate of the reactions to give us the equations, which is written as either a ln functions, which is the natural logarithm, or it will give us a and equations which relates the concentrations at different time point. And then from there, we will be able to determine the half-life of the reactions. Okay, so this plot here, it shows the potential energy of the reactant and the product. As you can see, the reactant has a very high energy in this example, and it needs to gain some energy which is higher than the initial amount of energy in order to proceed to the formations of the product which is lower in the energy. Reaction begins with encounters between the molecule. In this section, we consider two elementary approaches to the calculations of reaction rates. One is related to the gas phase reactions, and the other one is related to the reaction in solutions. Both of these approaches are based on the view that reactant molecules must meet one another to describe the interactions between them. So if two molecules, molecule A and molecule B, are to react, therefore they must approach each other closely to gain sufficient energy to break the existing bond and to allow the formations of the new bond. And such encounters is known as collision. When molecules collide, the kinetic energy and of this molecule can be used to stretch, bend, and eventually it will break the bond. Therefore, it can lead to the formations of new bond, or we say that it leads to the chemical reactions to occur. A reaction takes place only if the molecules have sufficient energy or it has achieved the minimum energy required. So if the molecule moves slowly with little kinetic energy, or if they collide with the improper orientations, then they do not react, while they will just bounce off each other. In the collision theory of bimolecular gas phase reactions, products are formed only if the collision is sufficiently energetic, or else the colliding reactant molecule will separate again. But in the solution, the reactant molecules may simply diffuse together, and then they will acquire energy from their surrounding while they are still in contact. There is a minimum amount of energy needed in order for the molecule to break existing bonds during a chemical reactions. If the kinetic energy of the molecule upon collisions is greater than this minimum energy, then bond breaking and bond forming occur. Therefore, they will produce a new product, which means if the molecules are moving fast enough with a proper collisions orientations, such that kinetic energy upon collision is greater than the minimum energy barrier, then a reactions occur. So this minimum energy required for a reaction to occur is called the activations energy. The activation energy can be achieved if the temperature of the reactions is increased, because at higher temperature the molecule will move faster. So higher temperature will promote the reaction to occur. Hence, it was common knowledge that higher temperatures speed up reaction, usually doubling the rate for a 10-degree rise. but the reason for this were not clear. In 1899, finally a Swedish chemist named Swan Arrhenius, he combined the concept of activation energy and the Boltzmann distribution law into one of the most important relationships in physical chemistry. If we focus on the meaning of these equations and neglect the A factor at the time being, first, this is a form of exponential decay. Then what is decaying here is the magnitude of the rate constant as a function of the exponent, which is minus activation energy divided by RT. And what is the significance of this quantity? If you recall that RT, is the average kinetic energy, it will be apparent that the exponent is just the ratio of the activation energy to the average kinetic energy. The larger this ratio is, the smaller the rate because of this negative sign. So this means that high temperature as T is large value and low activation energy when the EA is small value will favor larger rate constant. The rate constant value will be large and therefore it will speed up the reaction. And because these terms occur in an exponent, their effect on the rate are quite substantial. Activation energy. What is activation energy? Activation energy is the energy difference between the reactant and the activated complex. Or sometimes it is known as a transition state. So in a chemical reaction, the transition state is defined as the highest energy state of the system. If the molecule in the reactants collide with enough kinetic energy and this energy is higher than the transition state energy, then the reaction occurs and products form. In other words, the higher the activation energy, the harder it is for the reactions to occur. So by measuring the rate constant as a function of temperature, A and the experimental activation energy of the reaction can be determined, whereby A is the Arrhenius constant. From the Arrhenius equations, K equals to A exponent minus activation energy over the thermal energy, RT, can be written in a non-exponential form that is always more convenient to be used and to interpret graphically. It can be done by taking the logarithm of both sides and separating the exponential and pre-exponential terms to yield ln k equals to ln A minus EA over R multiply 1 over T. Therefore, by plotting ln k versus 1 over T, we will be able to obtain a straight line with the slope is equals to negative activation energy divided by R. So this enables a simple way for the determinations of the activation energy from value of the rate constant observed at different temperature. to this point, the pre-exponential term A in the Arrhenius equations has been ignored because it is not directly involved in relating temperature and activation energy, which is the main practical use of the equation. However, because A multiplies the exponential term, its value clearly contributes to the value of the rate constant and therefore the rate of the reaction. Recall that the exponential part of the Arrhenius equation expresses the fraction of reactant molecules that possess enough kinetic energy to react as governed by the Maxwell-Boltzmann law, and this fraction can run from 0 to nearly unity depending on the magnitude of the activation energy and also the temperature of the reactions. So in other words, A, the pre-exponential factor, is the fraction of molecules that would react if either the activation energy were 0 or if the kinetic energy of all molecules exceeded the activation energy. Meaning that if exponent minus EA over RT, this value here is equals to 0. So exponent 0 will become 1. Therefore, K will be equals to A. Okay, although this scenario is uncommon, but the rate of the reactions, the rate constant will be only depends on A. Real-world reactions are often not elementary overall. Most reactions occur in sequence of steps are called elementary reactions, each of which involves only a small number of molecules or ions. An elementary reaction happens in a single step and has one transition state. The rate law for an elementary reaction can be derived from the coefficients of the reactants in the balance equations, since an elementary reaction represents an actual interaction between reactant particles. You can only do this for one-step reaction. You cannot do this for overall reaction. The molecularity of an elementary reaction is the number of molecules coming together to react in an elementary reaction. Note that the phase of the species is not specified in the chemical equation for an elementary reaction, and the equation represents the specific process occurring to individual molecules. The phase, for example, usually we will see that the reactant, then we will have a bracket represent S for solid and then L for liquid or gas for gas phase. Usually for elementary reactions, in these equations we do not specify the state of the reactant. In a unimolecular reactions, a single molecule shakes itself apart or its atom into a new arrangement, as in the isomerizations of cyclopropane to propane. Okay, so the rate of the equations is equals to rate constant multiply A as the reactant. So this elementary reaction is the first order to the concentrations of A. In the bimolecular reaction, a pair of molecules collide and exchange energy. Atoms or group of the atoms or undergo some other kinds of changes. And it is important to distinguish molecularity from order. Reaction order is an empirical quantity and obtained from the experimental rate law, whereby molecularity refers to an elementary reaction proposed as an individual step in a mechanism. So in these bimolecular reactions, we have 1A react with 1B to results in the product formations. The rate of the equations is equals to K multiply A to the power of 1, which is the order with respect to reactant A, multiply reactant B concentrations to the power of 1, which is the order for B reactant, and the value of 1 for A and 1 for B, they were deduced from the equations, which directly from these elementary reactions equations, 1A plus 1B. If we have A react with A, meaning that 2A react to give us the product, the rate of the equations can be deduced from these elementary reactions as equals to K multiply the concentrations of A to the power of 2, represent the second order with respect to reactant A. And this 2 is deduced from the elementary reactions. Okay, so we can only do this where directly determine the order with respect to the reactant concentrations. We can do these direct determinations for the order if the respective equations is the elementary reactions. Else we cannot do this. So in addition to unimolecular reaction, bimolecular reactions, then we have the intermolecular reactions, which involve 3 different types of the reactant. Okay, so 1A react with 1B, react with 1C, results in the product formations, and the rate of the equations is equals to K to the power of K multiply concentrations A to the power of 1, multiply concentrations of B to the power of 1, multiply concentrations of C to the power of 1. The order with respect to the reactant A, B, and C are 1, which is they were deduced from the elementary reactions, okay, from these equations, 1A, 1B, and 1C. When experiments give a rate law that doesn't match a single step stoichiometry, the process must be multi-step, where it occurs in 2 or more elementary steps. A reaction intermediate is a chemical species that is formed in the elementary step, and it will be consumed in a subsequent step. So the overall rate is gated by the rate determining step. The slowest step in the reaction mechanism is known as the rate determining step. And this rate determining step will limit the overall rate and therefore determines the rate law for the overall reaction. One of the most important applications of kinetics is to the study of reaction mechanism, or the sequence or step by which chemical reactions occur. For example, consider the reactions of nitrogen dioxide with carbon monoxide. Okay, so based on the balance equation, we might hypothesize that this reaction occurs in a single collision between the molecule of nitrogen dioxide and also the carbon monoxide. In other words, we might hypothesize that this reaction is an elementary reaction. If that were the case, then the rate law would be based on the reactant coefficient in the balanced chemical equation, which can be written as rate equals to rate constant K multiply the concentrations of nitrogen dioxide to the order of 1, multiply the concentrations of carbon monoxide to the power of 1 or the order of 1. However, when this reaction is studied experimentally, the rate law is in fact observed to be rate equals to K rate constant multiply nitrogen dioxide to the order of 2. Since the experimental rate law does not match the one that derived by assuming an elementary reaction, we know immediately that the reaction must involve more than one step. Reactions that occur in two or more elementary steps, as I told you earlier, is called multi-step or complex reactions. We can use the experimental rate law to help deduce the individual steps that might be involved in a multi-step mechanism. Once the experimental rate law for the reaction is known, chemists can begin to devise and investigate possible reaction mechanism. So meaning that we have to determine the rate law first, after that to investigate what is the respective mechanism for the reaction. A possible reaction mechanism must meet the following two conditions. Number one, the equations for the elementary steps in the mechanism must add up to the overall equations for the reaction. Second, the mechanism must be consistent with the experimental rate law. Now let's refer to the same example where nitrogen dioxide react with carbon monoxide. The proposed elementary step 1 is nitrogen dioxide react with nitrogen dioxide molecule to produce nitrogen monoxide and nitrogen trioxide. And the second elementary step is as written here. We add both of the elementary steps. Okay, it will give us NO2 plus NO2 plus NO3 plus CO will result in the NO plus NO3 plus NO2 plus CO2. Okay, so the overall equations will become NO2 plus CO plus NO plus CO2, where the NO2 on the left cancel out with the NO2 on the right. Similarly, NO3 on the left cancel off with the NO3 on the right. Okay, so left only NO2 plus CO results in the product L of NO and CO2. Note that one molecule of nitrogen trioxide appears in both steps in the mechanism, but doesn't show up in the overall equation. In this case, nitrogen trioxide is a reaction intermediate, where it is a species that is formed in one step and consumed in a subsequent step. From the previous slide, we have shown that the equations for the elementary steps in the mechanism, when they were added up, it meet the overall equations for the reaction. So next, we need to determine if the two-step mechanism is consistent with the experimental rate law. To do so, we need to know which of the two steps is the rate determining step or the slowest step in the mechanism. Why? Because a reaction can occur no faster than its slowest step. The rate determining step effectively limits the overall rate of the reaction. It can be analogous to how a traffic jam limits the overall rate at which cars can move along a highway, even if other parts of the highway are clear. So we have to find out which elementary step is the rate determining step. For these reactions, elementary step 1 occurs slower compared to elementary step 2, where it takes 1 second for elementary step 1 to proceed and 1 times 10 to the power of minus 4 seconds for elementary step 2 to proceed. Therefore, step 1 will limit the overall rate of the reaction, and the rate law for this step will be the same as the overall rate law. So the rate of the reaction is equals to the rate determining step for the elementary step 1. Therefore, the rate determining step rate law is equals to K1 multiply concentrations of NO2 to the power of 1 multiply concentrations of NO2 to the power of 1 equals to K1 multiply the concentrations of NO2 to the power of 2. So it is a second order reaction. So just now we have seen that step 1 is low and step 2 is fast. Therefore, the observed rate law for the whole reactions mirrors step 1's law, which says that it determines the rate law according to the elementary reactions of the step 1 for the whole reaction. But when the slow step includes an intermediate where it doesn't involve in the example just now, if the intermediate is involved in the elementary reaction for the slow step, then we need a way to determine the concentrations of the intermediate. That's where steady state and pre-equilibrium approximation came in. Steady state approximation is applied in a situations whereby the intermediate remain constant for the durations of the reactions, where the intermediate in the reaction mechanism is consumed as quickly as it is generated. So the rate change of the concentrations of the intermediate can be approximated to 0. Therefore, we have these expressions, the rate change di dt is equals to 0. And we can use this to approximate the concentrations of the intermediate that are present during the process of reactions occur. With the use of steady-state approximation, we can find the rate law for a reaction with a fast and reversible initial step. In this method, we first write the rate law based on the slow step or the rate determining step. Then we eliminate any intermediates from the rate law. We use the fast initial step to solve the intermediate concentrations in terms of the reactant and the product concentrations. For example, in the reaction between nitrogen monoxide and bromine gas, the elementary step 1 proposed is as given here, and the elementary step 2 proposed is this one, and step 2 is much slower compared to step 1. So from this elementary step 2, because it is the slowest step, therefore it is the rate determining step for the whole reaction. And we can write the rate law as equals to K2 multiply concentrations of NOBr2 to the power of 1, where the rate order is 1, multiply the concentrations of NO to the power of 1. Okay, so in this rate law, it involves the presence of NOBr2, which is the intermediate in this whole reactions. So we have to apply the approximations to replace these concentrations of NOBr2. In order to determine the concentrations of the intermediate NOBr2, we can apply the steady-state approximations. So the rate change of NOBr2 with respect to time is equals to 0 according to the steady-state approximations. So this rate change can be determined from the reactions, elementary reactions, where the rate change of NOBr2 equals to K1 multiply NO multiply Br2 minus, because it has been used up, so in the reverse directions, multiply K minus 1 multiply concentrations of NOBr2 minus it is being consumed through the second elementary step, K2 multiply NOBr2 multiply NO equals to 0. By having these equations, then we can find out what is the respective concentrations of the NOBr2 as an intermediate. And having the expressions, we can substitute it into the rate of the reactions. Okay. Other than the steady-state approximations, there is another approximation known as the pre-equilibrium approximations. These approximations can be used when the first step reach equilibrium quickly relative to the product formations. So in former, we say that when K minus 1, the reverse directions, the consumptions of the NOBr2 is much more faster compared to the product formations in the step 2, okay, the K2. So K minus 1 is very much larger than K2. Then we can use the pre-equilibrium approximations. So A to form the intermediate is always near equilibrium, while from intermediate to the product formations is usually very slow. When we use the equilibrium relationship, the equilibrium constant K, capital letter K, is equals to the forward rate K1 divided by the reverse rate K minus 1. It is equals to these expressions here. Then we can do some rearrangement to find out what is the NOBr2 and substitute into the rate of the equations, which is deduced from the elementary step or the rate determining step. Okay, then we substitute into the rate equations for these intermediate concentrations, and eventually we will get these equations. Okay, so what is the difference between the pre-equilibrium approximation compared to the steady-state approximation? So when to use steady-state approximations and pre-equilibrium approximations? We use steady-state approximations more generally when the intermediate remains at low steady concentrations after a short inductions, even without a true equilibrium. While we will use the pre-equilibrium approximation when the first step truly equilibrate quickly and unbinding is much faster than conversions, which means that if the reverse of the intermediate formations back to the reactant, the rate is much more faster compared to the from intermediate turns to become the product formations K2. So these are the rate of the reactions that we derived just now using the steady-state approximations and pre-equilibrium approximations. The steady-state approximations can be reduced to the pre-equilibrium approximations if the value of K minus 1 is very much larger compared to K2. So if this one is very large, then K minus 1 plus K2 multiply NO will be approximate or close to the value of K minus 1. Therefore, the steady-state approximations can be reduced to the pre-equilibrium approximations. You will see that these two will be the same if K minus 1 is very large value compared to K2.